All right, welcome back to the Calibration Lab. Today, we're diving deep into the physics of what might be the most critical yet honestly frequently misunderstood component on a modern engine, the knock sensor. Now, you and I both know this isn't just some simple microphone you slap onto the side of a cylinder head. We're talking about a highly tuned acoustic guardian that lives right on the block, constantly working to protect your engine from catastrophic detonation.
So, in this explainer, we're basically doing a masterclass. Here's our agenda. We'll start with the piezoelectric crystal physics, move into mechanical tuning and resonance, then hit ECM signal processing algorithms. After that, we'll cover shielding and multi-sensor fusion, dive into oscilloscope diagnostics and failure modes, and wrap up with precision installation and torque. Let's get right into it.
All right, Section 1, the piezoelectric crystal physics. To truly grasp how this thing does its job, we've got to zoom way in, right down to the microscopic level inside the PZT ceramic disc at the heart of the sensor.
Now, the magic really happens at what we call the Morphotropic Phase Boundary, or MPB. We specifically engineer the PZT, that's Lead Zirconate Titanate, ceramic to sit exactly on this boundary. Why? Well, because existing in two crystal phases at the exact same time is the absolute sweet spot. In this precise state, the crystal acts like a massive electrical sponge. It yields the highest possible electrical charge when it gets compressed, putting out anywhere from 400 to 600 picocoulombs per newton of force. That is huge.
But here's the kicker. Raw, sintered ceramic, totally dead right out of the oven. We literally have to force its internal domain structure into alignment using a pretty intense process called electrical poling. First, we heat it way above its Curie temperature, somewhere between 150 and 350 degrees Celsius. Then, bam, we hit it with a massive DC voltage, talking up to 4 kilovolts per millimeter. As it slowly cools down, that electrical polarization gets permanently locked right into the crystal lattice. Now it's active. Now it can actually generate a signal.
But this highly engineered alignment isn't invincible. Far from it. Sustained engine heat actually causes those internal domains to naturally relax over time. It's a logarithmic process called thermal aging, and it slowly, almost invisibly blinds the sensor over hundreds of thousands of kilometers. Plus, severe mechanical shocks can completely randomize the structure, and reverse electrical fields, they'll destroy the alignment outright. But the big one to remember, if you expose this sensor to temps over 150 degrees Celsius, say by routing the harness too close to an unshielded exhaust manifold, you permanently destroy that crystal alignment. Game over. Moving on to Section 2, mechanical tuning and resonance. So let's look at how all this builds into an actual mechanical system. Because sitting directly on top of that piezoceramic crystal is a seismic mass, and it operates exactly like a highly tuned mass spring system.
I want you to consider a specific number, 10,160 Hz. That is the exact acoustic resonant knock frequency we'd calculate for an 86mm engine bore. And this frequency isn't just pulled out of thin air. It's strictly dictated by the physical speed of sound traveling through the high-pressure combustion gases inside that specific cylinder. A larger bore, like a massive displacement V8, is going to resonate and knock at a much lower, deeper frequency. On the flip side, a smaller motorcycle bore, that's going to knock at a much higher pitch.
So, to accurately detect those specific frequencies, we calibration engineers use exact mechanical damping ratios. The older, resonant sensors were deliberately underdamped with a zeta value of less than 1.0. This gave them this incredibly sharp, highly sensitive peak to listen for just one specific frequency. But today's modern multi-cylinder engines, they need something much more versatile. They use critically damped wideband sensors. By targeting a damping ratio right between 0.6 and 0.9, we get this beautifully flat, smooth frequency response stretching from 1 kHz all the way up to 20 kHz. This lets the ECM analyze wildly varying knock profiles across completely different cylinders, all in real time. But for this finely tuned mass spring system to actually hear the engine block, the acoustic coupling interface literally has to be flawless. The block surface needs a roughness, an R value of less than 3.2 micrometers. If there's even a single raised burr on the metal, it creates an asymmetric clamping pivot point. And worse, tiny concave air gaps or even microscopic patches of corrosion act as literal acoustic insulators. They will completely deaden those high-frequency 10 kHz vibrations from ever reaching the crystal.
Okay, Section 3, ECM signal processing algorithms. So how do our ECMs actually tell the difference between a catastrophic engine-ending knock event and just the normal chaotic mechanical noise of the valve train?
Well, that raw analog signal has to run an absolute digital gauntlet. First up, buffer, amplifying, and variable gain conditioning to normalize the voltage. Next, high-speed analog to digital conversion. We're talking sampling that waveform up to 200,000 times a second. Then, the fast Fourier transform, or FFT, kicks in. The FFT takes that chaotic sound wave and slices it into specific frequency bands, sort of like how a glass prism splits white light into a rainbow. Finally, the ECM calculates a knock intensity index, which normalizes that exact knock signal against the engine's ever-changing background noise floor.
And to get that ultimate analytical precision, the algorithm strictly gates its listening window. It's exactly like a sports photographer waiting for that split second to snap the perfect photo. The ECM completely ignores the sensor during noisy events, like say, exhaust valve slamming shut, and it waits for absolute internal silence. It's programmed to only open its digital ears during a precise crankshaft rotation window, usually right between 10 and 60 degrees after top dead center, because physically, that is the only window where a destructive knock event can actually happen.
All right, Section 4, shielding and multi-sensor fusion. Processing the signal is one thing, right? But getting that fragile millivolt signal safely through the engine bay to the ECM, now that's a whole different nightmare. Just think about the sheer electrical violence inside an engine bay. You've got 40,000 volt spikes blasting from ignition coils all over the place. To survive that, modern platforms use a 4-wire differential signal system. The ECM reads the signal as a balanced pair, mathematically subtracting the negative voltage input from the positive. It's actually the exact same phase inversion trick your noise-canceling headphones use. This mathematically cancels out common mode noise, essentially turning the twisted pair harness into an invisible shield that rejects interference from injectors and coils by an astonishing factor of up to 10,000. Now we also have to fight mechanical signal attenuation, because acoustic shock waves die out really fast as they travel through solid metal. It's especially bad in dense cast iron, where the signal rapidly decays, dropping 20 to 30 decibels every single meter. Aluminum blocks are actually much better acoustic conductors, but even then, the signal still drops off significantly over distances of about 400 millimeters. Because of this rapid decay, larger engines absolutely require complex multi-sensor arrays and advanced signal fusion algorithms just to pinpoint exactly which cylinder, way at the far end of the block, is actually detonating. Section 5, Oscilloscope Diagnostics and Failure Modes. Look, when things go sideways in the bay, as a professional, you have to know exactly what the ECM is seeing at the sensor level so you can diagnose it properly. The DTCs tell a very specific story if you know the physics. A P0326 performance code, it rarely means the sensor is just totally dead. Actually, it usually points to terminal fretting corrosion increasing the circuit resistance, or maybe thermal aging of the PZT disc lowering its sensitivity. On the flip side, a continuously low input P0327 almost always means engine vibration has caused the harness to chafe against a hot bracket somewhere, creating a hard short to ground. And a P0325 circuit fault, that points to a completely open circuit or a totally dead PZT element. But the ultimate truth? It's always on the oscilloscope. A totally healthy sensor is going to give you this beautiful high-amplitude exponential ring-down burst, cleanly timed, strictly after top dead center. But a failed unit is going to hand you something completely different. You'll see a total flat line if it's an open circuit, a constant 0 volts from a dead short to ground, or just this continuous, ugly wall of clipped noise if the internal PZT element has shorted out against its own metal housing. The visual evidence is just undeniable.
And here's something you really need to remember. Modern wideband sensors typically show an open loop on a standard digital multimeter, unlike the older resonant ones that would read a specific baseline between 3.3 and 4.7 kiloohms. So you literally cannot test them with just a simple continuity check. You've got to run a strict professional diagnostic checklist. Get in there and inspect the connector closely for fretting corrosion. Verify the harness is routed well away from extreme exhaust heat. Do a physical block tap test with a brass hammer while you're actively monitoring the AC millivolts on your scope. And of course, always verify that your block ground path resistance is well under 0.1 ohms.
Finally, Section 6, Precision Installation and Torque. Let's wrap up with what is absolutely the most critical and, honestly, the most misunderstood aspect of knock sensor installation in the entire industry.
Think about this for a second. How much does over-torquing a mounting bolt actually shift the sensor's internal frequency? I know it's super common to think snugging it by feel is fine, or maybe giving it a little extra quarter turn for safety won't hurt. But let's actually look at the math and physics behind that clamping force.
Over-torquing the bolt physically squeezes that internal piezoceramic element harder,
This drastically ramps up the mechanical stack clamping force, which directly increases the system's overall mechanical stiffness. Now, if you think back to our mass spring equation, a higher mechanical stiffness mathematically forces the natural frequency higher. Literally, just a 10 Newton-meter overtorque can shift the sensor's resonant peak completely out of the ECM's tuned listening window. Congratulations, you've just made the engine completely deaf to knock. And if you go the other way, undertorquing the bolt introduces friction hysteresis noise, which just muddies the signal completely.
So to guarantee accurate acoustic coupling, your workflow has to be rigorous. No cutting corners. First, file and clean that mounting surface until the raw is under 3.2 micrometers. Second, make absolutely sure the bolt threads are bone dry. No thread locker, no sealants. Liquids act as acoustic dampeners. Third, route your shielded harness far away from EMI sources, like the alternator. And fourth, always, and I mean always, tighten that bolt strictly using a calibrated torque wrench. No exceptions.
As we wrap up this explainer, I want to leave you with one final provocative thought. If the core physics demand this level of absolute mechanical precision, where just a few extra foot-pounds of torque can literally blind the ECM to engine-destroying detonation, are we truly treating these microscopic acoustic guardians with the exact respect they deserve in the shop? Something to think about. Thanks for geeking out on the science with me today. Keep asking those questions, and I'll catch you in the next one.